Okay, so I'll try to give you a sketch about the digital model, which of course is very peculiar and complex according to this scenario. So it was completely reworked with reference to previous approaches, and I tried to make no compromises on the digital side to represent everything we needed to represent. So let's first consider a traditional digital approach. The starting point is the autograph document, the text carrier, and that's our material evidence, a document with the potential to represent multiple versions of a text as it contains annotations which imply changes to it. So ideally we have multiple texts derived from it, even though they are abstractions defined by our interpretation of the carrier. So in this traditional approach, the digital model reflects this set of texts, adapting models designed for a single text with multiple witnesses to represent multiple versions of a text. So we create many documents for each of these texts and use markup, usually TI, to connect them. In each text, the tags mark portions which have been deleted or added with reference to another version. And that's similar to a diffing operation between two texts. We compare them, and whenever they diverge, we annotate the deviation type. So this allows scholars to reuse models and tools created for traditional philological scenarios where they compare text witnesses. And in fact, they mostly use markup from the critical edition TI module. And often this is fine. Anyway, in our scenario, it's difficult both for the higher scale of complexity and for the conceptual nature of this representation. So first, in our case, we have no final version at all, but often deeply annotated carriers integrate a constellation of alternative texts, even dozens of them, representing true work in progress. Second, a comparison-based approach is challenging to implement scale up, because the more the versions, the more the connections among them. And even more difficult it is for the audience to grasp the creative process behind all the variants. We align versions side by side, providing the details of each difference, but we have to mentally figure out the creative process behind these differences. That's because this approach focuses on the effects of the process represented by the carrier. The carrier with all its chaotic annotations is the witness of a creative process in the author's mind. And all the variants we collect and align are just the effects of this process. In a digital edition, anyway, time can no longer be our enemy, but our ally. The same time which accumulated all these changes on a text, making it a puzzle for scholarly interpretation, can be the key to a more effective model of the creative process. So we need a dramatic focus shift from the texts extracted from the carrier to the process which generated them, which is implicitly witnessed by the carrier. We thus move from the effects, the texts, to the cause, the process, and the text-making process generates all the different texts we can deduct from the carrier, and it's reflected by the annotations found on it. Now, a process can be described as a sequence of actions in time. With reference to text making, these actions are editing operations, like deleting, adding, replacing, moving, swapping portions of a text. So in our process model, we start with a base text and then apply one editing operation after another, accumulating their results. The first operation outputs what we call version 1. With version here, we just represent in outputs. Version 1, in turn, is the input of the next operation, which outputs version 2, and so forth. We thus follow a time thread whose effect is the production of progressive alteration of the base text. The process via its operations is the focus, while text is just the effect of this process. So given the high level of detail provided by structuring the process into multiple operations, this implies that we want to regard every single output as a self-contained and complete text stage. Most versions are just steps along a path which leads from one alteration stage to the next one. So we can say that each operation generates a version as its output, but only some of these versions are considered as alteration stages. That is a sort of waypoints along our transformation path. These correspond to the multiple texts traditionally extracted from the carrier. And note that with this focus shift, such a model can represent multiple texts even when there is no final stage at all. From an abstract point of view, all stages coexist and are equally valid alternatives. So we are back to our constellation of texts. These correspond to text alteration stages in our model and are like stars derived from the same nebula, which is the creative process we focus on. So the weaker light from these stars and from the nebula itself is the effect of this generation process. The bright stars are our text alteration stages, and the background light of the nebula is the annotations scattered all over the sheet and hinting at the operations which generated text versions. The light is what got captured by our carrier, so we might see it as our telescope, which allows us to look at the light coming from the past. Of course, telescope power is limited. Observation provides facts and some clues, and our interpretation does the rest. So the astronomer here is the scholar who interprets the carrier to reconstruct the creative process behind it, just like the genesis of a constellation could be reconstructed from the nebula, including it. Essentially, data supplied by our carrier is a set of signs. Some of them represent text. In most cases, they are letters and punctuation. Others can be any sort of graphical sign, hinting at a specific editing operation. So for instance, a stroke on a word hints at. So these other signs can be anything: lines, arrows, shapes, callouts. There's no limit to what can be drawn on the sheet. All these signs represent the more objective layer of data. Then it's up to our interpretation to deduct the operations and their order, reconstructing the process. So this scenario is defining the requirements for our digital model. At the base, we have our carrier, the material document. Our interpretation of it aims to reconstruct the process witnessed by that carrier, frozen at a given point in time, like a photographic snapshot. It is this process that generates all the multiple texts virtually present in this snapshot, operation after operation. And snapshot is right the name we give to the set of all these data, the signs on the carrier, the editing operations, and the virtual texts, which are their effects. So the carrier is just the material support of these signs, while signs and all the abstractions derived from them, operations and versions, are the snapshots. Now, modeling such a snapshot is difficult as we need to compose multiple tensions: the objective layer of the carrier versus the subjective interpretation of it, the graphical dimension of the signs versus the textual nature of the signified data, and the single uniform nature of the creative process and the multiple text versions, which are its effects. So let's tackle one problem at a time. First, we require a single data structure to represent multiple texts. If we look at the text as a sequence of characters, we might say that to build a new version, we need to combine these characters in a different way, possibly adding new characters. For instance, consider a text like "this is a sample text." We can represent it as a set of graph nodes, each representing a single character, chained into a sequence. Nodes are connected by links, which carry the identifier of the version they represent. As this is our base text, all the links have version 0, and these links connect the characters to form our text. Whenever an operation is executed, it generates a new version with a progressive number, adding new links tagged for that version. So say we delete the word sample. We want a single data structure for any text. As we model text as a sequence of nodes, the most efficient way to represent a change in it is just to recombine the same nodes in a different way. A new combination implies the addition of a new set of links which connect the nodes. For the next version, which is 1 in this case, most of them will be equal to the previous ones, except that to delete the word sample, we create a bypass from the character at its left to the character at its right. The new set of links connects the space before sample to the initial letter T of text. So we didn't touch the existing nodes, we just added a new set of links to connect them in a different way. This results in a new version of our text, that is, this is a text, and that's version 1. We created it by just adding links and reusing nodes, guided by a delete operation. So a single data structure, named chain, contains two sets. The first is a set of nodes, one per character. In a set, items are not ordered, we simply put nodes in it. Just like with ink and paper, once we add a character, it stays there forever. We then combine character nodes in different ways to build sequences which represent each text version. These character nodes are connected with a set of tagged links, and each set of links corresponds to a version. Here you see the tags which connect each pair of nodes to the base text, which is version 0 in this case. The way we deal with this data structure is via editing operations. In our example, it was a delete, but whatever the operation, it translates into additions to the chain. We add new tagged links and possibly new nodes when the operation implies new text. So for delete, we add a new set of links tagged for the next version, 1, bypassing the portion of text which has been removed. Thus, our chain design is very simple. It consists of just two sets, nodes and links. Operations are the way we use to change the chain, and they just add links and nodes to the same sets. So again, let's say we now want to represent another version. That is, this is a test. This operation adds a new node for S, replacing T, and a new set of links for version 2. The links are almost equal to those of the previous version, except for the fact that we bypass the old T and connect the new letter to its neighbors. This time we have a replacement operation, but the logic and the model is the same. We thus solve the tension between single data structure, our chain, and multiple text versions. To extract any of the versions, we just follow the path defined by the links for it. If we follow the 0 path, we get this is a sample text. If we follow the 1 path, we get this is a text. There's no limit to the number of versions, and adding 1 implies only adding links and sometimes nodes. So compare these with having a full distinct text for each version and comparing them all. The key to this efficiency is right the focus shift from the effect, the versions, to their cause, that is the process, structured into operations. Additionally, the model allows us to represent not only text, but also annotations on it. As our data is focused on the process which generates text, there's no text to start with. So we can just add tags to it, like in XML. Rather, our metadata is linked to operations, which then inject them into generated text. So the snapshot contains base text and operations. These operations add nodes and links into the chain, which in turn generates all text versions, while also injecting operation metadata into text, thus annotating it. Such metadata is linked to operation via so-called features, and a feature here is just a name-value data pair linked to a node or a whole version. Each project can provide its own set of features. We thus solve the tension between multiple and single texts using the chain, and we can now consider the one between subjective and objective data layers. In this architecture, there's a clear separation between these layers because at the bottom there is the material carrier with its signs, which for the most part are beyond subjective interpretation, and that's our objective layer. Then we build a model for the creative process structured in operations, which feed a single data structure, our chain, and these can generate text versions with annotations. Annotations come from operation features injected into nodes or full versions, and among them, rendition features can be used to represent the graphical appearance of operation on the diplomatic side. And this takes us to the tension between textual and graphical data. While we generate texts from process operations, we also need to represent their graphical appearance. And to do this, we must consider the types of our signs. The most obvious type is the base text itself. For instance, here, font is part of it. Other signs are added later. So one of them is a diagonal line crossing these words, and this line hints at a deletion of it. So the meaning of this sign is an editing operation. It literally hints at it. That's why we call these signs hints. Hints are the visual counterpart of editing operations. Another type of sign is then the word meant to replace fund, that is funder, written below it. And this is added text. So we are removing Wund and adding Wunder. In simpler terms, we are replacing Fund with Wunder, and that's our operation. The line hints at it, and the text added below it is written below. We thus define three types of signs: the base text, the text added by operations like add or replace, and the hints which visually correspond to them. Both added text and hints are also known as added elements because they are added later with reference to the base text. So, as everything is based on operations, their visual counterpart is in operation metadata in the form of rendition features. For instance, here this operation has a diagonal line as its visual and adds text, the word funder, below and to the left of its reference text. So here two features will be used, one for the hint, the diagonal line, and another for the position of the added text. So we just say in our model diagonal line and below and left, and then it's up to the software to do the math to size and position all the elements in our visualization. To this end, the visualization software also uses a catalog of visuals in sets, a set of drawings, which are our hints, like lines, box, circles, any kind of drawing, to pick and reuse, and a set of animations, like fade in, wipe right, and so forth. Because time is a crucial aspect of this model and its presentation. We focus on the transformation process happening during time, step after step, replaying what we reconstruct as our process. And in visualization, time means animation for each state transition. So animation here is a semantic factor. In a traditional approach, we deal with a previous stage and the next one. We then represent this transformation in terms of its effects. So comparison shows us that in stage 2, something maybe has been deleted and something has been added. The process remains hidden behind its surface effects, And when faced with tens of stages, figuring it out becomes hard. In our approach instead, we replay all the steps between stages. So we first transform text 1 by deleting some text. Visually, a cross hint enters the stage via an animation, and then we add some other text, which visually means this new text entering the stage, again via another animation. So we can literally see the text transforming under our eyes. That's why not only each operation is linked to many visual hints, but also each hint is linked to an enter animation. Everything flows in the continuous flux of time. So focusing on a dynamic process rather than just comparing static stages is closer in this sense to the reality of the text-making process. And the same holds for both the textual and graphical sides of the model. In real world, once you write on a sheet of paper, the sign stays there forever. You can draw a stroke on it, overwrite it, or whatever else, but yet the sign is there, and we are just adding new signs. And the same happens for our model. On the text side, the chain structure contains a set of nodes and a set of links, and operations just add items to those sets. Once an item is added, it stays there forever. On the graphic side, any sign we add to our drawing surface, whether it's text or shape, gets accumulated operation after operation until the final stage, where all the signs are present. So again, once a sign is added, it stays there forever. So this visualization is very powerful, but also complex to design and relies on a sort of visual grammar, which instructs the software to display things as we want them. To this end, we have seen that we define 3 types of signs: the base text, here in green, text added by operations, in red, and any other signs, the hints, here in blue. This classification allows us to define the rendering logic for each group so that we just say what to draw to the software rather than how to do it. As for text, base or added, we simply draw one character after another until line end and then continue on the next line. Position and text properties can anyway be changed by rendition features. Differently from base text, the added text has an arbitrary position defined by a rendition feature. Here you see a list of rendition features. You will find them also in your booklet. And using them, you can change text properties, offset positions, and add more transformations like rotation, scaling, and the like. These features may alter the default behavior of our signs, which differs according to their type and follows a predictable logic. As a general rule, all added elements refer to base text elements. And that's because we are effectively annotating base text. So every added sign, like a line for a deletion or a letter for an addition, is meaningful only with reference to the base text. So that's why their position is defined with reference to base text elements. For instance, in our sample, uppercase T is above the lowercase t of this, while the S added after show is above and right of it. The reference text is the text affected by the operation. For instance, the lowercase t, which is replaced by the uppercase T. Now, imagine drawing a box to include this reference text. We call this the reference text bounding rectangle, or RBR for short. So for the initial word in this mock text, the RBR is this orange rectangle you see around it. Now let's consider the position relative to this rectangle. We might place our element so that its bottom right corner touches the upper left corner of the rectangle, that is at northwest, or we can center it at north, and so for other positions, northeast, west, east, and so forth. Additionally, we might position the element inside the rectangle, touching its corners at the top or at the bottom. And finally, we can position the element with reference to the center of the rectangle. And that's the origin position, which is the default one. You can see the origin in action for the line on top of the I word before show. Here the line is the diagonal of a rectangle, sized and positioned just like the RBR. And the effect is drawing the line over the whole text being deleted. Also, we can then shift any of these relative positions via horizontal or vertical offsets. So if you look at the top left epigram number, 12 in this case, this is effectively offset to left and right. So this is a Cartesian plane. The origin is the top left corner. X values increase rightwards and Y values downwards. And correspondingly, Y decreases upwards and X leftwards. So in the case of 12, both offsets are negative, which pushes this number to the left and to the up of our sheet. So having seen the position of added elements, let's see their size. For added text, the size adjusted that resulting from drawing the text with its rendition features, font, size, style, and the like. Hints instead are sized just like the rectangle and then scaled if requested. So when we want to draw a line on a text, like in this deletion, the default size is just what we need as we cover the whole reference text. Instead, when we want to box the word hints, we scale the rectangle up while keeping it at the center of the rectangle. And the result is effectively boxing the text along all its edges. So hints are the visual counterpart of operations besides the added text when present. So each operation can be linked to 0 or more hints. Of course, we could never predict all the possible hints and describe their forms in advance. That's why the set of hints is not closed, but open to expansion. So hints are not directly embedded in operations, but rather they are picked from a catalog of visuals. And in this catalog, each hint comes with its metadata. Among them, there is a free drawing representing its form, whatever its complexity. The use of the catalog is due to the fact that, of course, often the signs of a carrier can be grouped into classes. While each sign is a unique historical act, its form can be reduced to a more abstract type, reused many times. So for instance, here we have a diagonal stroke raising to the right, used to represent deletions and occurring at each deletion. Similarly, another hint type is the box around a word. And yet another one is a textual annotation above its reference text to represent word reordering. And finally, a different textual annotation, underlined, rotated, and offset, is another type again used for numbering. So we group all hints into more abstract types and provide a catalog of their visual representations, together with its properties like rotation, scaling, offsets, and the like. Whenever we need such visual, we just pick it from the catalog via a rendition feature. So as the visualization is time-focused, each hint is also linked to an animation, which defines its entrance, rather than just letting it appear abruptly. And in turn, such animations like fade-in, wipe right, and the like are typically reused, and thus they belong to a similar catalog. So just to let you know, here is how a hint looks like in the catalog. This is a diagonal stroke hint. Its SVG property contains code defining its shape using an XML dialect SVG used to represent geometrical shapes. So you can see here a group, which is the root element of the hint, including a line element, which is our diagonal shape. The line's color is defined by a placeholder variable, which gets resolved from a feature with the same name. And in this way, we can contextually change the color of the same hint when using it. And finally, the animation is fade in and thus points to the corresponding code in the animation catalog. The animation appears like this. That is a small JavaScript code fragment which is used to animate the hint's entrance. So here we are animating the opacity, that is from 0, which means totally transparent, that is invisible, to 1, which means totally opaque, that is fully visible, in the duration of 1 second. So this is a fade in, and whenever we need it, we just pick this from the catalog of animations. Any other hint has the same model. Here you see a box, it contains a rectangle, the relative position is centered, its scale is 110%, which makes the box bigger than the reference bounding rectangle and thus avoids it touching the edges of the text inside it. Another one is a note, which contains text, whose content is defined by a placeholder variable, and the note is placed above the rectangle, but you can override the position via other features. That's again another variation with an offset shifting it down because we want an interlinear note. And another example of this flexibility is the hint for the epigram number at the top left corner. Here we use an underlined text with custom color and text placeholder positioned at northwest, shift to the left and top, and scaled to 200%. So whatever the form, hints have their shape and their own properties to customize their behavior. Additionally, hints can include an element which works as the handle for the whole drawing. In this case, this element's bounding rectangle is used for positioning the whole drawing. And this feature can be useful when you have to displace a portion of the drawing, like the line of a call-out. Finally, another feature can be used to displace added text or hints, because occasionally these elements can be positioned far from their reference text. For instance, the word hints in this mock text, which replaces another word in the third line, which is stuff. Both these words are boxed to connect them, despite their distance. And in this case, the positioning logic doesn't change. We just have a displacement feature which specifies another base text as the reference. And this has the effect of displacing it as required. So that's a fairly abstract model we have seen right now, and it's designed, of course, for reuse. Now I just show you how it works using our sample epigram so we can understand all this stuff and how it works in a real-world case. So consider this symbolic representation of the epigram. That's what we want to visualize. And here we have two ends, as we have already seen, one in orange, another in red. We start with orange, and the first operation is a simple change in punctuation. At the end of line 4, we replace the semicolon with colon. Then we reorder words in line 5, and this is done by just adding numbers on top of the words. Finally, we add an annotation at the left of the first line, stehen, and that's the correct handling for the word künstlichen. And this ends the alteration stages by the orange hand. Now the red hand's operations start, first clarifying the intent of the previous hand by inserting st at the right place. We then add a dot on the eye of Weich and confirm the reordering in line 5 by redrawing the numbers in red. And then in last line, we replace dan with d, remove bist und before the second bist, and add und before ein Engel. Finally, later, an epigram number was added with black ink. So let's try to describe all these in our model for both textual and graphical layers via operations. So the first operation outputs a new version, which is 1, and it's just an initial setup to indent lines, because as we have seen, base text layout has no indentation in itself, so we need to customize it before start. That's why we use here an annotation operation, which only adds features without changing the text. The text in the orange box here is the textual representation of the operation in its syntax. And of course, we don't enter operations in this way. We have a user interface for this. In these slides, I'm using the text only because it's a more compact way to represent the operation. The operation starts with the coordinates it affects, and that's because every character node has its numeric identifier. Then an operator, here colon, specifies its type. and the features follow in square brackets. So in this case, we had a horizontal offset to the first character of each even line in the epigram, thus indenting them. The offsets feature contains multiple pairs, each with character identifier and offset value. And also we constantly add a log feature with a short description about the intent of the operation to make the code more readable. Now let's start transforming the text proper, replacing the semicolon with a colon, which is the first operation we reconstructed. Note that visually this is complex because the hand here traced a stroke on the comma only and then added a dot above the existing one to mean a colon. So a common feature here, as you can see, explains these to end users with text, but we also want to visualize this. So we first pick a hint, the diagonal stroke down, which represents the stroke on the comma. But then we want to display only one dot above it, even though we are replacing the semicolon with colon, which has two dots. To this end, we add a feature which changes the operation's value. This allows us to display another text instead of that provided by the replacement operation, a dot instead of the colon. This, anyway, is for visualization only. The text is still transformed into a colon. It just appears as a dot. So in the end, we get to write a colon, just like the hand did it on the sheet. So we can faithfully represent our visuals while still correctly encoding the text changes, that is the replacement of the dot with the colon. Next, we are going to reorder words in line 5. We thus replay the reconstructed actions, adding a hint with a number above each word. So the first is mention, and we add a hint whose content is specified by the not feature, and here is just the number 1 in orange color. Numbers are added one at a time, but they all belong to the same logical group, thus building a sort of macro operation, which is named reorder. And the same happens for all the other numbers. So that's number 2 above hub, number 3 above ich, number 4 above the count. We're just doing what the hand did at that time, number 5, and number 6 above tire. So until now, we just added signs on our virtual sheet to represent annotations hinting at a reordering. Now we effectively transform the text by moving it so that it matches the order specified by the numbers. So here we move ab hic count before tire. No hints here because we just added them before. Finally, for the orange hand, we add the annotation sten at the left of the first line. That's not very perspicuous, but it is hinting at the fact that the word künstlichen should be corrected in its orthography. So with the output of this operation, we complete the first alteration stage, corresponding to changes by the orange hand. So here, a special property named version internally assigns alteration stage 1 to the output of this operation. We thus promote this specific output to an alteration stage. So all the previous outputs, our so-called versions, were just steps towards this alteration stage. Now the other hand, the red one, first makes the last correction explicit by adding st at the top of a callout sign. This sign is represented by the hint I named half psi because it resembles half of a Greek letter with its name, while the added text appears above, north, a bit smaller, font size, and offset up, offset y, as you can see from the features. Also, the color now is red and no longer orange. The red hand now adds the missing dot above the I of Weich. So this is just a hint named I dot written over the letter. Then the red hand confirms the word reordering already suggested by the previous hand by literally redrawing the same numbers with red ink. So again, we do the same, replaying what happened number after number, but this time the color is red and the macro operation name is reorder2. Also, we have a reason feature, which says that the reason of this annotation is a confirmation. So the same happens for all numbers, the 2 above up, and the 3, and the 4, the 5, and the last one, 6 above tire. Note that here we do not end the macro operation with the actual change in order, because this was already done before. Here we are just confirming the change which happened before. Finally, we move to the last line. Here we replace done with D. The hint here is a horizontal stroke on the deleted word, while the added text appears above it when positioned north and a bit smaller when font size 20. We also do a couple of related deletions. We delete the first beast from the last line, again with the same horizontal stroke. And then und before beast ein Engel, again same horizontal stroke. Finally, we add und before ein Engel, and here we have another hint named snake for its shape, acting as a call-out. Note that this hint among its properties already has a vertical scale equal to 200%, and that's required, and it's part of the hint, because hints are sized as their rectangle, which should make the snake just as tall as the text it is annotating. Instead, we want it to extend above and below the text, and it is accomplished by the scale and the center position. Also, the added text is a bit smaller and red. So this completes the second alteration stage. So a version feature tells us that the output of this operation corresponds to that stage. After all this, later the epigram gets numbered, and this epigram gets number 37 with default black ink. So we have a final annotation operation above the first line of the epigram at a certain distance from it, whence the vertical offset, with a not hint and a value equal to 37 plus a dot. So we replayed all the actions of the text transformation process, generating a new text output at each step, promoting a couple of these outputs to alteration stages, and accumulating all the signs corresponding to our operations on our virtual sheet. Additionally, another layer of abstraction can make operation metadata even more efficient, because we have seen abstract yet still lower level features which directly specify things like position, color, font size, and the like. Our approach also allows for higher level features, acting as a shortcut to multiple lower level features. So for instance, consider the numbers later added to some epigrams to define a collection by specifying their relative order in it. Now, in many cases, this number was written in a single session by a single hand, and thus it has a similar appearance and position. So we can define a higher level feature named epigram number, which gets translated into multiple lower level features. And these tell to pick a specific hint, set its text to a value equal to the number, position it northwest, offset to left and top, and scale by 200%. So a single feature implies all these features and provides an even more compact way of representing visuals, so the user will just pick from the list epigram number rather than picking all these features from the list in the user interface. Of course, as we have seen, besides the rendition features, we also have other features which represent specific metadata we want to inject in the text. So here you can see a list of them, but you can find them in your booklet. And to create a snapshot, as we have seen, we have a full web-based editor, which allows you to define all the operations and their metadata in a graphical user interface, and also allows you to represent higher level entities beyond our snapshots. But this is not the topic of this seminar. Presently, I'm working on creating the visualization engine I have described you in the model. And I can show you the sample epigram using the new visualization engine, even though it's rather a draft until now. But it can show the intended user experience where you see the text transforming under your eyes, operation after operation, in a rich and interactive environment. So before starting this sort of movie, let me call your attention on the main parts of the user interface you will see. You will see a top toolbar, versions list and text to the left, details at the bottom, and the text visualization proper at the center. The software component has been designed to be used everywhere, from a static web page to a full web application. And to this end, it adopts a standard web technology, the custom web components. And thanks to it, placing a full visualization into an HTML page is as simple as adding an element to it, which is a universally compatible element, whatever language and technology you use. So every other project will be able to visualize snapshot data by just importing this component. Now, the toolbar you will see contains navigation controls, and this allows you to move around to the next or previous versions or alteration stages, or directly to the first and last one. There is a button to toggle the slideshow where the visualization advances automatically, and you just watch the movie with options also to cycle it or play it reversed. Zoom controls, a download button which allows you to get an image from the current visualization, the description of the last executed operation and the current version indicator, plus optional custom buttons which can be added by the host page. The versions list contains all the text versions from top to bottom, and those staged, that is the alteration stages, are outdented in that list. And each version also gets automatically a color. If you click on a version, all the visual elements belonging to it are highlighted in that color. If you click on the arrow button next to the version, you move to that version directly. The version's text then shows the text of the current version, and that's very useful because at times reading the visualization can be difficult. For instance, deletion is marked by a stroke, but the deleted text is still there, like in real words. Or reordering can be suggested by numbers above words, as you have seen, and it would be up to the viewer to imagine the resulting text. So here instead, you can see the plain text resulting from all the transformations up to this point. Also, you see the text of the previous version and an automatic comparison of both with colors representing insertions and deletions. So this lets you grasp what happened to the text at a glance. You can also pin a version so that the current one compares to it instead of the previous one, or invert the comparison direction, copy the text, zoom it, and toggle word wrap. Finally, the details pane shows a full summary of the last operation with all its features, and it also shows the global features injected into the resulting version up to this point. Also, when you hover the mouse on any text element, each letter of our text, you get the list of features injected into it, together with an enlarged version of that element. So this is not only a fully animated visualization, but it also provides high interaction and full details about each portion of the text at any time of its transformation. So let's try to see it, if I can let it work. I uploaded the demo this morning on the train, so I hope it works, but just to show